Alright, hey guys, we're going to go through titrations fairly quickly. Most of it's just review. It's stuff that you already know about. You have multiple types of problems you've dealt with so far. Titrations kind of bring them all together because you have to know how to approach multiple points during a titration using ice boxes, Henderson-Hasselbalch equation, salt hydrolysis, etc. before, during, and after boxes. So really briefly, titration is just a volumetric analysis experiment. So you're talking about how you know something about the titrant, like the volume and the molarity. That's why it's called also known as the known, because you know everything about it. And then there's something that you don't know, like for example, the volume of an analyte or the molarity of an analyte. So there's going to be something else that you don't know. We call this one the unknown in an experiment. The point that's the most important point, I think, probably of an acid-based titration is the equivalence point, where you have equal molar concentrations, but I also like to really enforce that it's the equal moles of acid and moles of base, because that's important to know, especially if you have something that's not a 1-to-1 mole ratio. You need to go back and maybe look at the balanced chemical equation before you can figure out where the equivalence point is. The three types that we'll mainly work with are the easy ones, strong acid, strong base. That's just going to make sure that you have the BCE, and then whenever you have the BCE, you can use mole ratios to determine what you need. Also, we'll use weak acids and strong base, weak acid, strong base, and then strong acid, weak base. Both of these are going to allow for us to use partial neutralization, and partial neutralization is just where one of the strong base or the strong acid halfway or partially neutralizes that weak acid or weak base. That's going to allow for the creation of a buffer, because we all know that buffers are the combination of a weak acid and its conjugate. Well, as a strong base or strong acid are neutralizing things, they're creating salts, when those salts contain the conjugates that we wish to look at for the Henderson-Hasselbalch equation. So we'll look at those when we get there. So this is just a basic generic equivalence titration curve with a strong acid and a strong base. The reason that you know it's a strong acid and a strong base is because you're starting off very low and you're ending very high. Very low is 1 or down. 13 or 12 and higher is also very high. It also has a special point, the equivalence point, at pH of 7. That's because after a strong acid and strong base have reacted, and you've used up all the strong acid and you used up all the strong base, you've made a neutral salt. A neutral salt does nothing for the pH. It's the fact that you have water present, where the water creates H3O pluses or H pluses and OH minuses, each in the same amounts, which is going to allow for a pH of 7 when you do negative log of 1.00 times 10 to the negative 7. This is all review. You know this. Another thing I just want to make sure that you understand is that if you ever have to draw what's in a burette or in a flask or something for a titration, if it is strong, such as this strong base or this strong acid, you need to ionize everything, 100% dissociation. None of it stays together. Don't draw the molecules together. Draw everything as an ion. All right, so this is the first of 3 or actually 9 questions I'm going to go over. They're very brief, but I'm going to show you my work for it so that you can copy what you need to or try it and then look at the answer. So if you'd like to pause right now, see if you can do this, do so. I will give you a hint. You need to write out your balanced chemical equation, and you need to do a before, during, and after box for each one. So here's mine. Maybe. Sorry about this. All right, so for the first problem, for this strong acid, strong base titration, you've got sodium hydroxide and hydrochloric acid. The hydrochloric acid is the part that's already inside of the flask that you're using for your titration, and the sodium hydroxide is the titrant it's being added. You guys know how skilled I am at putting the document camera up. Okay, so for the first part here, we've got, before the equivalence point occurs, we have 2.5 millimoles of the acid, because you had 25 milliliters and 0.1 molar solution. 25 times 0.1 is 2.5. You also are adding 10 mils of 0.1 molar solution, so that gives us 1 millimole. This is your limiting reagent. You minus, you add, you make NaCl and water. You also have left over excess hydrochloric acid. So if you have that left over, you take your millimoles of that. Don't forget that you need to divide by the total milliliters before you can get the actual amount in terms of molarity that you will then plug into your log function to get a pH of 1.37. So even though we've added a little bit, just a little bit of strong base, it's still a strong acid, so it's still fairly low in terms of the pH. The second example is when we added 25 mils of 0.1 molar sodium hydroxide. So you'll see on my work here, but you'll see that we have equal amounts, 2.5 millimoles, 2.5 millimoles of both the strong acid and strong base. Both of them run out at the same time. We are left with 0 here. We created sodium chloride and water. Like I said earlier, anytime you have a strong acid, strong base titration, it makes a neutral salt. This neutral salt has nothing to do with the pH. It's mainly, and I have my salt hydrolysis proofs right here, no reaction, no reaction. It's the water that has equal concentrations of both of the hydronium and the hydroxide, which is going to allow for us to get pH from 1.0 times 10 to the -7th. That's the only thing contributing to the pH of 7. Last one. I feel like I'm going over this fast, but that's mainly because this is easy. You guys know how to do these charts. This is just a quick review if you've forgotten. Sodium hydroxide and hydrochloric acid. We still have our 2.5 millimoles of this, same old, but we've got 35 mils of 0.1 molar sodium hydroxide that we've added. The 35 moles converts to 3.5 millimoles, minus your LR in this case, which is your acid. Your acid is not going to be present anymore. We have an excess amount of 1 millimole of the base, which contributes 1 OH per base, and we divide it by the total, which in this case was 35 plus the 25 originally of this acid. That gives us 60 millimoles. We take the hydroxide concentration, we do 14 minus the POH to give us a 12.22 molarity. I'm sorry, pH. So this curve is a standard curve. It starts off at about 1, ends at about 12, and it has an equivalent point of 7. Oops, let me go back here. All right, so that's why this curve looks like this. What if I give you a different scenario? We have a weak acid and a strong base. First of all, note to self. You need to know that if you have a weak acid and you're starting with the weak acid and you know how much you have of it, like in this case, you can actually get the initial pH. You can take this 0.1 molar of the acetic acid. You can do you will know the Ka, which we probably have memorized now. You can do an ice box. You can determine the hydronium present when that partially dissociates. Then you can do negative log and you get the pH. So you can get the very, very, very beginning pH. Since this is weak, it's going to be a pH of 2 or more. But in this situation, we have another scenario where we have some of the sodium hydroxide has been added. This is before the equivalence point. We have a point where we have 25 mils of the sodium hydroxide and we're starting off with 25 mils of the weak acid. This only works out because we have the same molarity for both those weak acid and the strong base. This is at the equivalence point. And then after the equivalence point, when 35 has been added, we're going to see that we have a fairly high pH. So let's walk through this one. My skills on the document camera again here. Okie dokie. There we go. Oh, and then I'll show you about the buffer part here too. That's what that big note is for. All right, using our knowledge, our vast knowledge again, we have our starting point of a before, during, and after chart, where you start off with your 2.5 millimoles, because that's 25 times 0.1 for the weak acid, and you're starting off with your sodium hydroxide of 1 millimole, because it's 10 times 0.1 of the strong acid, strong base, minus what your limiting reagent is. In this case, it's your limiting reagent is your base. You end up with weak acid left over, 1.5 millimoles, and you've created a conjugate base of 1 millimole. So in this case, you recognize right now, you need to think about this. When you see that you have leftovers of a weak acid and a conjugate base, then that means you're able to use the Henderson-Hasselbalch equation. Do not go and do an icebox now, because that's going to take you more time. So if you're looking at the Henderson-Hasselbalch, you do pKa plus the log of the conjugate over the weak, and you have the Ka given to you. The ratio is given to you in your after part of the box. You get 4.57 as your pH, and you'll notice that it's very high in comparison to like a normal acid, because the weak acid it's neutralizing faster because of the strong base being so much stronger than the weak acid. Not all the acid is going to be neutralizing the base, so the base kind of wins in the situation and causes the pH to jump quite a bit. Next example, we have the acetic acid still. We're still adding sodium hydroxide, but we're adding a little bit more sodium hydroxide. we added 25 mils of 0.1 molar, which was 2.5 millimoles. Oh my gosh, that's the same as the acetic acid. So both of these run out at the same time. Nobody's the limiting reagent. Both of them are the limiting reagent. Depends on if you think of the glass as half full or half empty. But regardless, both of them run out, only creating the acetate ion as a result. And water, but we don't care about water. So 2.5 millimoles of that is added, so 2.5 millimoles of that is created. This is important. You'll notice that since this is the only thing left, you say, oh my gosh, how do I find the pH? Well, the pH this is actually sodium acetate. We know how to find the pH of a salt. In this case, the sodium came from sodium hydroxide, so that's a no reaction, we don't care. The acetate ion came from a weak acid, so that's the anion that is important. So since this is acting as a, this will act as a weak base in terms of accepting a hydrogen from H2O, you're going to reform your acetate and hydroxide. But one big point that everybody forgets is we are currently in millimoles of the before, during, and after box. You need to divide by your total solution volume in terms of milliliters. That was 25 plus 25, which is your 50 milliliters. That's going to allow for you to get the molarity. Molarity has to go in an icebox. So since this is an icebox and you're going to be using a K value, you have to use concentration. So we get acetate is 0.05 minus X, acetic acid is X, and hydroxide is X. When you see that it's acting as a base, you remember you have to go find your Kb. Well, Kb is Kw divided by Ka. You get 5.56 times 10 to the negative 10th. And when you plug your stuff in, your products of reactants, X squared over 0.05 minus X, neglecting X. Solve for X. X is equal to 5.3 times 10 to the negative 6th, which was your hydroxide concentration. Plug this into pH, equals 14 minus the POH to give you 8.72. Notice that we have jumped yet again. Last one here is after, oopsies. Oh, okay. After you've added 35 milliliters, of the 0.1 molar solution, you end up with excess amounts of the hydroxide present because that is now in your excess reagent. That's your strong base. Strong base does not, the weak conjugate base does not compete with the strong base at all. The strong base has ultimate control of the pH. 1 millimole divided by your total, 35 plus 25 is 60. That's 0.1666 molar. Plug that into your POH, so 14 minus POH is equal to 13.2. All right, let's look at this one. So when you draw this curve, it's going to look something like, sorry, I didn't mean to pause that, but this is going to look something like this. You start off at a higher pH of about maybe 2. This has a little loop that it kind of happens initially. Oops, it doesn't go back down though. It continues to go up, and then you hit your equivalence point, and then you're back at your normal pH. So this was about a 12.2 or 13.2. The equivalence point was about 8.7. The equivalence point is right in the middle of the vertical section. The vertical section halfway up is going to be the equivalence point. The equivalence point here is basic because of the strong base added. Another thing to notice is that I drew this kind of loop / curl, all curly little area. Every single time you have a weak acid, it's always going to start off that way. It's because it's neutralizing a little faster to begin with, and then it levels out. This leveling out part is the result of the buffer zone. There's a buffer there at that point, then the partial neutralization of the weak acid, which creates the conjugate base, and we have some stable pH happening there. After that, everything is controlled by the strong base. I'm going to pause and upload another video after this one for the rest of this lecture.